Okay, today we're going to be talking about energy of reactions. And so we start off with going back to what we already covered, which was that those reactions can be endothermic or exothermic, as in heat comes in or heat leaves. And we touched this a little bit in the last video, but let's dive into a little bit more about energy. And so in order to do that, we have to talk about the law of conservation of energy, which you guys who have taken physics or maybe in grade school you've heard about this, which is that energy can't be created or destroyed. But in chemistry, we specifically apply that to the chemical reactions. During a chemical reaction, energy is neither created nor destroyed, which really means that we have to look at the bonds in a reaction. And so what we're really getting at here is that if more energy is needed to break the bonds than is going to be released when you create new bonds, then you're going to have to get that from the surroundings, right? Then your reaction is going to absorb. And if the opposite is true, it's going to give off. And how we do that is by looking at bond energies. And we're not going to get heavily into this, but I do think it's worthwhile to touch on this and just talk about the basics of what happens in a reaction. So if we were to look at the reaction of H2, or hydrogen gas, plus I2, all right, or hydrogen plus iodine, it's going to go form two HIs, okay? And so the other way to put this is that you have this HH bond, and you're going to react it with this II bond, and in doing so, you're going to make two HI bonds. All right, and so there is energy associated with each of those concepts. And so when we talk about that, HH has a bond energy of 436, and it's kilojoules per mole. All right, and then II, right, iodine has a bond energy of 151. And again, the same thing, kilojoules per mole. Okay. Well, then when you come over here, each of these things is going to have the same bond energy, all right, which is going to be in an HI bond. We get 297 kilojoules per mole. And so when we're talking about looking at this, we can see that when you break those HH bonds, you're going to need 436 kilojoules of energy to do it. To break the II bond, you're going to need 151. And so what we're really saying is over here on the reactant side, we need a total of 587 kilojoules of energy. All right. So we're going to need 587 kilojoules. And over here, because we're creating two HIs, we're going to have 594 kilojoules. All right. That is, released essentially because we're stabilizing these atoms. And we don't have to go into it crazy, but since in this case you are releasing more energy than you are consuming, okay, this will be an exothermic reaction. It's going to give off just the slightest amount of energy. All right. Now, we don't need to go into all this. We're not going to be going through and doing heavy calculations to look at it, but this tells you kind of what is needed to do this reaction. And then on the flip side of it, what is produced. And it gives you a look at what happens energy-wise within a reaction. Okay, so now that being said, we can then go back and look at, well, with this, well, we now have our endo and exothermic. So a reaction which heat's absorbed, well, that means that those products are not releasing as much energy as is needed. And then in exothermic, it's like that one where we have that excess, we can get rid of it. All right. But the real heart of our energy discussion here is to get into the concept of, well, what is it that causes reactions? What causes them? How do they occur? And, so when we look at it, we can define a reaction as, or say it occurs when a bond is broken and new bonds are formed. All right. And it's after they rearrange. So we don't have reaction if oxygen, separates, we break a bond and then they come back together. That wouldn't be a reaction. All right. But if those oxygens separate and orient themselves in a different way, then that's a reaction. And so we want to know, well, what causes this? And at the heart of it is, it's this concept called collision theory, or collisions. It's truly just these things collide, and because they do, reactions occur. All right, so bonds are broken when these molecules collide with enough energy and in the right orientation. So when these things collide, okay, with enough force behind them, they're going to then cause a reaction to occur, whether that's just breaking down, opening up, rearranging. We can get into all the different types of reactions this way. But those bonds are going to be broken and then rearranged and reformed when they collide with enough energy in the right direction. So we just talked about with those bonds like HH, it takes 436 kilojoules per mole. Well, that kind of translates down to, for one individual H2 molecule, you need X amount of energy. And so when these things collide, if they don't collide with that energy, no reaction occurs. There is no splitting. You can't break the bond. And so then we start getting to, well, what could influence how these things interact? And so that's what we're going to ask now. Can anything affect the rate at which these collisions occur? And so when we talk about reactions, we talk about reaction rates. Or when we have a reaction, what is the rate of reaction? The speed at which that reaction occur, or that the reactants become the products. How fast does it happen? That's the rate. And so we want to know, well, what could affect the rate? And we're talking about collisions. So what we're really asking ourselves is, how can we make more collisions with more energy? And the question, and what we're going to look at is, well, there's two things. I mean, there are more than that, but right now we're going to look at, well, there are two things. Well, the first thing is kind of simple. Concentration. What if we just increase the number? Well, it's kind of simple. As the concentration of the reactants goes up, there's going to be more collisions. The more collisions, the greater the chance of a successful collision, and therefore the faster the rate. Imagine if we measured, well, how many times do students bump into each other as they walk around the classroom? And we went from having 10 kids in the classroom to having 100 kids. Well, they're going to bump into each other more. And so if each one of those is a chance at reaction, there's more chances and therefore more reactions. And the rate will increase because of that. Similarly, if you wanted to slow down the reaction, you could make it a lower concentration and right away you would slow it down. All right, so then we want to get into, well, temperature. Well, what's happening with temperature? Well, as you increase that temperature, you are quite literally adding energy, right? Temperature is the movement of these molecules, right? So as they're in there, they're going to move around faster. And what we're going to see is that because of that, not only are there more collisions, but they're at a higher level of speed, a higher energy. So not only are you increasing the number of collisions, you're also increasing the energy at which they collide, which again makes more successful collisions, more successful reactions, and therefore faster reaction rate. All right, in order to really look at and think about the collision theory here, you just have to kind of jump down in that molecular level and think about, well, what would increase these concepts? And when we're talking about liquids, right, we could talk about things like temperature, we could talk about things like concentration, or, we could even get to things like what you do, agitation, stirring, anything that's going to cause greater collisions, all right, to happen. The two we're looking at here are temperature and concentration, but there's an innumerable number of things that have an effect on reaction rates. These are just a few.